This section will be discussing the periodic trends associated with ionization energies and electron affinities. First of all, we have to define what ionization energy is. Shown here is a sodium atom in the gas phase in which energy has been added, promoting the valence electron to the n equals infinity level and removing the valence electron. This is typically referred to as the first ionization energy. It turns out that if you add more energy, it is possible to remove other electrons from the atom. In the case of sodium, these would be electrons in inner shells, and so these would require quite a bit more energy to cause an ionization. So, as an example, the first ionization energy for sodium is 496 kilojoules per mole of sodium ions in the gas phase, whereas the second ionization energy is 4,562 kilojoules per mole, quite a bit larger because of the removal of an electron from one of the core of the inner shells. Shown here is a plot of the first ionization energy for the various elements on the periodic table. You see on the x-axis the atomic number for each of the elements, and on the y-axis the first ionization energy in electron volts, which is also an energy unit. The first thing to notice is that going from hydrogen to helium, there's a quite dramatic increase in the ionization energy. This is essentially the effect of adding the additional proton in the nucleus and the lack of shielding of the two valence electrons for helium, so that both of the valence electrons feel essentially a 2+ charge and cause the electrons to be attracted to the nucleus more strongly than in hydrogen. If we go to the second period, starting with lithium, you'll notice a general increase in the first ionization energy when going from lithium up to neon. This is also reflected in the third period when you go from sodium to argon, and likewise in the other periods, with some interesting little glitches in between. In particular, then, if we then focus in on what happens when we go and look at elements in the same group, if we look at the alkali metals, lithium, sodium, potassium, so on and so forth, you see a general decrease in the first ionization energy. This is because as the valence shell gets farther and further away from the nucleus, it is less and less energetically costly to remove the valence electron from the atom. So you see a general decrease in the first ionization energy. This is true for any of the groups on the periodic table. The trends in terms of the going from left to right in the periodic table, you generally see an increase in ionization energy due to the increase in the effective nuclear charge. And we discussed that previously when it came to dealing with both size and with the ions associated with these elements. Also, the glitches that are seen in, say, going from lithium to neon, if we go from beryllium to boron, you actually see a slight decrease in the ionization energy. This is a result of going from the S subshell to the P subshell. The P is always slightly higher in energy than the S, and therefore it makes it a little bit easier to ionize the boron as compared to beryllium. The other little glitch is seen when you go from nitrogen to oxygen, you see another decrease in ionization energy there. This is the spin pairing effect that you would observe by following Hund's rules in the orbital diagram. And so after you go and put 3 electrons into the p orbitals for nitrogen, you are then forced to pair the electron for oxygen, which is energetically somewhat costly. So just to emphasize this point again, as you go down a group, the atoms get bigger. The valence shell is further from the nucleus because the n value has increased. And as a result, it becomes a little bit easier to ionize a larger atom with the same valence electron configuration. When you go from left to right, across a period, generally the ionization energies increase with 2 exceptions. The first exception is the going from the S to P, from beryllium to boron, and then the second is when you have the spin pairing effect and the half-filled shell if you follow Hund's rules for the orbital diagram. Shown here is a 3-dimensional plot of the first ionization energies for the main group elements, and you can generally see that the atoms that are the largest, so for example cesium, also have the lowest ionization energies. It most easily has its valence electron removed. Generally, there's an increase in ionization energy as you go from cesium up to lithium, and you see that in each of the groups. And then likewise, if we go from lithium to beryllium all the way over to neon, you see the general increase in ionization energy from left to right. This means that the atoms in the top right-hand corner of the periodic table generally have the highest ionization energies, and atoms that are in the lower left corner of the periodic table have the lowest ionization energies. Shown here is some data to help reinforce the importance of the noble gas electron configuration. So for example, if we compare the abbreviated electron configuration for sodium to that of its ion, which has got a closed shell configuration and is very stable, in essence the valence electron for sodium is removed and forms the very stable ion. In the case of magnesium, there are 2 electrons in the valence shell. The removal of 1 electron is not stable. There is no magnesium 1+ ion that forms stable compounds. But if we remove 2 electrons, we then end up with a noble gas configuration, and it is very stable. If we look at aluminum, there are 3 valence electrons. The removal of the 1 electron from the p orbital does not form a stable ion, whereas removal of both of the s electrons produces the stable 3+ ion, which has the electron configuration of neon. Here is the ionization energy data. You can see that for sodium, removal of the first electron is energetically not that costly. To remove 2 electrons from sodium, however, the second electron would have to come out of the core, and that requires quite a lot of energy. Therefore, that is not energetically a favorable process. If we look at magnesium, there are 2 electrons that can be removed without too much energy expenditure, but the third electron would have to come from the core, and that's quite a big jump in energy. If we look at the aluminum, we have 3 electrons that are fairly easily removed, whereas removal of a 4th electron requires considerably more energy. So this helps explain the isoelectronic series and the stability of the noble gas configuration. Likewise, if we look at all of the data for the first and second period elements, we see this general um, pattern of energetically costly removal of core electrons. You'll also notice that the first ionization energy um, is generally increasing from left to right. This is also true for all the other ionizations. And it turns out that as you get further and further to the right, it's less and less likely that the atom will lose electrons, and more likely that we will then go in the opposite direction to get to the noble gas configuration by having these atoms gain electrons. So it turns out that nitrogen is basically the last element that undergoes any kind of loss of electrons to form positive ions. And so that is essentially the limit of the ionization energy that forms stable situations.